Welcome, everybody. It's our pleasure today to introduce Mikhail Katz, who will be telling us about extremal spherical polytopes and Borsuk's conjecture.
Thanks very much. Thank you for the invitation to speak. It's a great pleasure for me and honor. So this work is joint work with Facundo Memoli and King Song Wang. And basically the motivation of what we're doing is a hope to maybe find counterexamples to Borsuk's conjecture. Now, the general Borsuk's conjecture was already disproved by Kahn and Kalai almost 30 years ago. So what are we trying to do? Well, the conjecture was proved in rather high dimensions. And then eventually people brought down the dimension in which it was, they found counterexamples. But the conjecture is still open in small dimensions between 4 and 63. The lowest dimensional counterexample is in dimension 64. So we describe a potential source of counterexamples in these smaller dimensions. And we do that with a kind of, there's a significant component of this work is computer work, sort of downward gradient of the diameter functional on the sets of points on the sphere. So that's what we'll try to explain. The truth is that most of the talk is going to be about the two-sphere, where Borsuk's conjecture has been proved. But it's sort of a way of illustrating how one might go about looking for counterexamples in higher dimensions. We'll say a little bit about higher dimensions also. So let's start with the unit n-dimensional sphere, and which will denote Sn. And Y is going to be a subset of Sn. And we're interested in finite subsets. We're interested in finite point set configurations on the sphere. And when we talk about diameter Y, we're always speaking about the diameter with respect to the geodesic distance on the sphere. So let's start with a few definitions, and then eventually we'll get to what kind of computer work is involved. So let's define a taut set on the sphere. A finite set is taut if the convex hull of Y contains the origin. Another way of putting it is that there are coefficients that are positive coefficients, positive or zero, such that the linear combination of the points in the set is vanishes. Okay, so the origin is contained in the convex hull of the set. So there is a theorem of Jung, which is actually equivalent to the proposition that's stated here, that if the set is taut, then its diameter is at least this magic number, arc cosine of -1 over n plus 1. So in the case of the circle, that's 2 pi over 3. In the case of the two-sphere, that's arc cosine of minus 1/3. So it's something smaller. And these numbers go to pi over 2. They're bigger than pi over 2, and they approach pi over 2 as dimension tends to infinity. So in any case, there's something interesting that happens for these sets with a diameter limitation, that, as we will discuss in the future. So here's one corollary that will be used in the sequel to give you an idea of what kind of thing is going on here. Suppose that we have a subset of the sphere, a taut subset, which diameter is slightly bigger than the required minimum here. It's less than the cosine of -1 over n. So then these are very special configurations. They're necessarily linearly independent, or in any case, any subset of n plus 1 of them is linearly independent. In other words, there's only one relation between them, and all the coefficients are positive. So this is an immediate consequence of Jung's theorem. So just think of a non-degenerate tetrahedron. Think of a non-degenerate tetrahedron inscribed in the two-sphere of diameter less than 2 pi over 3, which is again talking about the Euclidean, not the Euclidean, but the spherical diameter on the sphere. We're talking about the 4 points which are the vertex set of a tetrahedron. Okay, so let's just go quickly over the proof. If the dimension of the span is less, then it's supposed to be if it's only n, then it lies on that means that it lies in a hypersphere. And then by the previous proposition, this diameter has to be at least r cosine minus 1n, which contradicts our hypothesis. So that proves the first claim. And the second claim is that if one of the coefficients is 0, then the remaining set of points is literally dependent, and that contradicts our hypothesis, the first part of the proposition. So the mental picture we're supposed to have here is that we have a regular, is a simplex in a sphere. And think of it as a perturbation of a regular simplex. Regular simplex certainly satisfies our diameter bound, and then we can perturb it and get interesting configurations that are still in the class of subsets that we're talking about. Of course, we're going to get much more complicated configurations, and we'll see, than just the regular simplex. Okay, so let's introduce some terminology so we can talk about these sets. We're interested in the magic number, which is diameter of the set. And so we will say that 2 points in the set are co-maximal in the sense that their distance is equal to diameter. And so we'll say that 1 point is co-maximal with respect to the other. And we will be interested in this notation co-max, which is a subset of the points of y which are co-maximal with y. So in the case of a regular tetrahedron, the co-maximal point of each vertex is just the 3 other vertices. Just the 3 other vertices. We will have more interesting examples in the sequel. So let's introduce another piece of useful notation, this gamma dot. If we have 2 points which on the sphere with distance less than pi, then there's a unique geodesic between them. And so we can consider the unit tangent vector to the geodesic at the point x. Maybe I should have included a picture here. In any case, we're going to get to some interesting pictures. And so now we have an interesting notion here. Suppose we have a subset of the sphere not containing antipodal pairs. So we want to exclude the situation when the geodesic is not unique. We say that y is held in place, little y is held in place by the set y if the set of comax vectors is taut in the tangent space at the point y. So in other words, the directions are going in, the directions leading from y to comaximal points sort of are pointing in all directions. You can't beat them. You can't make a small perturbation to decrease the diameter. That's the idea here. So the set of these vectors, these tangent vectors, is supposed to be taut in the tangent place at the point. And we say that y is point-wise extremal if every point of y is held by y. So again, the only example we have right now is the regular tetrahedron, but we'll see more interesting examples in the sequel. So let's see what happens in the case of the circle to get a feeling for what this notion how it translates into the geometry. So for the circle, any regular odd polygon, the set of vertices of any regular odd polygon is an example of such an extremal configuration. So a triangle, pentagon, 7-gon. So these are easy to see that these are extremal in this sense. And the converse is also true. If you happen to have a point with extremal subset of the circle, then it's the set of vertices of an odd regular polygon. It couldn't be an even regular polygon because it then would contain a pair of opposite points, which would give you a very big diameter, which is not allowed. So here is a proof. I don't know if I need to go over this, but in any case, the point is that if a point is held by y in this case, then both points at distance d from it have to be inside the set. So both directions have to be present. And therefore, the configuration is invariant under rotations by d, where d is the diameter of the configuration. And once it's invariant, then we know that d over 2 pi has to be rational. And then it shows that the set contains the set of vertices of a regular polygon. And once it has this, and once it contains it, then it couldn't be, you couldn't add anything else to it because that would increase its diameter. Okay, so that's what we have. That's what we're supposed to retain here from this proof, that in the case of the circle, you get a nice family of subsets, which are regular odd polygons, which are extremal in this sense. In the case of the circle, they also give you an optimal packing with an odd number of points. But on the other spheres, the extremal configurations are not really related to optimal packings, except for except for the case of the tetrahedron. Okay, so now let's look at some examples. Let's construct some examples. So these
let me just pause for a moment. Okay, so I thought there was a question, but I think this person wants to postpone it. But are there any questions that folks would like to?
Oh, sorry, I see that there are chats. Okay.
No worries. There's no questions.
So I have a quick one.
Okay.
So when you look at this gamma dots, is it only between comaximal points or just all the rest of the points in Y?
So the gamma dots are the directions to comaximal points by definition.
Only to comaximal points.
Direction towards comaximal point. I hope that was clear. I guess maybe it wasn't clear. In any case, that's
now it's clear. It's clear. Okay, thank you.
Good. Right. So in the case of the regular odd polygons, you get both directions to the 2 points at maximal distance in both directions on the circle. So if you look at the Soviet star, so each point is connected to the points at maximal distance. I don't know if it's Soviet or Chinese, but in any case, this star shape is what the graph of maximal distance looks like in the case of these polygons. 7 gon, 9 gon, etc. They all look like these starry things. Okay, good. So let's try to describe some examples. So it turns out that there are interesting configurations on the spheres of these extremal subsets. And eventually we're going to use them to generate new examples by computer. That's the idea that's the idea here. We want to, certain configurations we can construct, but then using sort of blindly following the diameter flow, we're going to construct other configurations that we wouldn't know how to construct without the computer. So that's what we're going to get to eventually, I hope. I see time flies. So let's sort of the 2 constructions. One simple construction is pyramids. This doesn't really produce new examples. And then the second construction is stacks. And that will produce new examples using the computer, as we will see. So let's go quickly over the pyramid construction. So let's start with the hypersphere inside our SN, and the pointwise extremal set there. For example, the regular odd polygon inside the circle, and then we can use that to build configurations on the 2 sphere called a pyramid. So the idea is simply to choose a horizontal section of the sphere, such that the distance from the North Pole to this level is the same as the distance among points of the configuration in the hypersphere. So for example, if you start with a pentagon, you get a pyramid over a pentagon. But the bottom of the pyramid is actually below the equator. That's the important thing here. It's an interesting, these 6 points of a pyramid of a pentagon is actually half the points of a regular inscribed icosahedron. This will not be needed in the sequel. It just happens to be the property of this configuration. But in any case, we're talking about the 5 points below the equator, not above the equator of the icosahedron. Okay, so now suppose we have 2 points at maximal distance. Then the 3 points, which is the North Pole and the 2 comaximal points in Y prime, which is the original pyramid, which is the original extremal configuration. They form the vertex set of a spherical equilateral triangle. And then applying the theorem of cosines, we get this kind of relation. Sort of a mysterious relation, arc secant of the secant of diameter -1. That doesn't happen to falls out of the theorem of cosines. So this way we get the family which we denote AK. Afterwards, they're going to be BK, CK, and DK. But the first family is the simplest one And that's just these pyramids. Good. So we have a picture here of a pyramid. Here's, for example, the pyramid that I mentioned before. That's can be thought of as half of a icosahedron. If you take the vertex set of this pyramid and also the antipodal points, together you get 12 vertices of the icosahedron. Okay, that's not really necessary for the Hemsha, for the continuation, for the sequel. Okay, so now here's a more interesting construction, a stack construction that we'll be able to use to generate new examples. So we start with a digon, which is a spherical lobe with an angle beta at the top. And then we build a stack so the procedure here is that we use a certain distance and start walking on the two. So again, what is a digon? A digon is just the spherical convex region contained between two longitudes. Or as Kingston prefers to call it, the meridians. I call them longitudes, okay? So then you start working on the alternating sides of the longitude, and then out of that, you build a spherical configuration with interesting properties. So what are the interesting properties? You get, there's a lot of, it's a little technical here. So here's basically, you start walking on the alternating sides of this digon until you get to the South Pole. You calibrate your distance so you get to the South Pole after a finite number of steps, after an odd number of steps. And then what you get is a configuration we call a stack, which consists of a North Pole. The North Pole is included. And also you get at levels, at K levels, for a fixed number K, then you're going to have a K configurations Y prime. There are parallel K triangles stacked parallel to each other. Or in high-dimensional spheres, you get you get simplices. Let's just take the simple case of the two-sphere. Then you get K triangles that are stacked. And let me just give you, so let's skip all of the details. So this is just how to calculate them. Let's just get to sort of cut to the chase. And here's the simplest example of this stack. Here we have one triangle, and here we have another triangle, and you have the North Pole. Altogether, you have 7 points. So that turns out to be an extremal configuration. And again, it's not an optimal packing. It's an optimal for a different property. It's not the not the maximum of the minimal distance, but rather the minimum of the maximal distance, locally at least. And for the other stacks, you're going to have K parallel triangles at K levels. Okay, so this is the family that's more interesting. Now, just to say a word about higher dimensional situation, you get on the 3-sphere, for example, you will get tetrahedra, a bunch of tetrahedra, and again you have the North Pole plus a bunch of tetrahedra, which are placed at an appropriate level to get an extremal configuration, according to the formulas that I skipped. Okay, good. So now we get. So now let's. I'd like to try to present some theory behind this. So let's capital D. Let you know by capital D, the set of capital D of S2 with D, well, little d, the set of finite subset of the sphere of diameter less than D. And then the interesting value D was for us. We're going to be the first accumulation critical value, which is 2 pi over 3 in the case of the sphere. And then the Hausdorff distance is a metric on this space. And the diameter extremal sense, which is in notion slightly different from pointwise extremal, a subset is called diameter extremal. If it's, what I want to say is it's a local minimum of the diameter functional, but it's a little more general than that. It's up to a quadratic term, it's a local minimum. So its diameter is going to be less than the diameter of nearby sets up to a little o function. So in other words, those who don't like a little o's, you can write it as a limit. The diameter of y prime might not be literally bigger than y, but it's almost bigger. If you divide by the Hausdorff distance, then the limit is going to be bigger than or equal to 0. For who you know, limit. And so it turns out that if the diameter, if a point set is diameter extremal, then it is pointwise extremal. It has the nice properties that we described on the previous slides for pointwise extremal sets. Every point is held by y, and in fact, you get much nicer properties of the configuration. They give you anti-self-polar tetrahedra, as we will explain soon, hopefully. So then it turns out that these, first of all, let's give another definition. A subset is called literally a minimal set if its diameter is literally less than any nearby set. And then it turns out that, in fact, every minimum is, if you look at this magic value, 2 pi over 3, which is the first accumulation point of critical values, then every diameter extremal set is actually a minimum. And so this is, it could be that the transition from this theorem to this lemma is actually the main connection of this talk to the theme of this conference, because here it's a kind of Morse theory with a non-smooth Morse function. You get, because every critical point is a minimum, then it has to be unique. And each connected component has to be unique. So that's what the corollary says here. The lemma, in each connected component of this big set, there's only one minimal set, which is a diameter extremal. Not only diameter extremal, but it's actually minimal. And so now we can use real algebraic geometry, sort of standard things, semi-algebraic geometry, to get a bound on the number of connected components, simply because things here are defined by algebraic polynomial inequalities. So we don't really need to go over too many details here. There, you get certain bounds, and you get a finite number of connected components, and therefore theorem, you get finite number of diameter extremal sets whenever d is strictly less than 2 pi over 3. Okay, let me just skip this lemma and let's look at these stacks that we saw on the previous page. So the idea is, I wanted to get to these deletions. So the idea is as follows. You can start with these stacks, which are very predictable configurations. Certainly not counterexamples to Borsuk's conjecture. But then something slightly magic happens. If you delete suitable points from the stack, that's what you note here, dE of bk. Bk is the family of stacks that I described on the previous slide. Then it turns out that if you delete certain number of points, and then you apply gradient flow of the diameter function, downward gradient flow, then you get a new extremal configuration. And then with properties that are quite unpredictable, you wouldn't have guessed it beforehand. So that's the idea here. You want to delete a few points and then flow with the flow. And here is a key property that you could ask, well, if you flow with the diameter flow, maybe the points will coalesce and you won't get anything interesting. So the point is that they don't coalesce. So it turns out that they don't coalesce because of a simple property of separability here, which has nothing to do with the classical property of separability. We say that the subset of a sphere is separable if for any 2 points in y, there are 2 other points such that the 4 tuple is taut. And it turns out that you can delete points from these stacks and get separable configurations. So then you're guaranteed from the start that when you flow with the flow of the diameter functional, the points do not coalesce and give you new interesting configurations. And in particular, you get a proposition that there are infinitely many pointwise extremal sets up to this magic value of 2 pi over 3, which are not contained in neither of the 2 families that we started with, the pyramids and the stacks. There are infinitely many examples there. And so for example, let me give you an example of a deletion. If you start with this stack, the first non-trivial stack, and you delete one of the bottom points, and then you apply the gradient flow, then what you get is a pyramid. Now, a pyramid is not a very interesting configuration. We already had it in the family AK. You get a pyramid on a pentagon. But for all other k, for k bigger than or equal to 3, if you start with bk, you get a new configuration. Pretty soon we will try to see some pictures of the configurations that you get. So let's try to go over this idea of anti-self-polar polytopes. First of all, let's denote, as is traditional, in the literature, denoted by Fi, the number of I faces of a polytope P. And then the string of integers F0 up to Fn minus 1 is called the F vector. And Lovash introduced a certain type of polytope in his paper many years ago. We will call it anti-self-polar because that's the most descriptive definition. So here we have three basic properties. P is inscribed in a sphere. It's circumscribed around a concentric sphere. And there's also a bijection between vertices and facets. So opposite each vertex, there is a facet. And opposite each facet, there is a vertex. That's what these anti-self-polar polytopes look like. So they're called anti-self-polar because of this property here. You can think of, because the polar of P is equal to minus P with respect to a suitable sphere of a suitable radius. That's why they're called anti-self-polar. And these are the interesting configurations. Lovash proved some interesting things about it. That if you take by the way, if you don't assume this diameter bound, then the extremal configurations are not necessarily self-polar. But within this diameter, they are necessarily self-polar because of this example of an anti-prism. This is, I don't know how successful this picture of an anti-prism is, but in any case, it's a counterexample that it's not that an diameter extremal configuration is not necessarily anti-self-polar. Okay, so so much for that. Okay, so of course, to try to get to Borsuk, okay, we're of course interested in the diameter graph, of Y. So we're interested in the diameter graph because we're interested in the chromatic number of the diameter graph. And okay, the chromatic number, everybody knows what the chromatic number is, how many colors it takes to color a graph, where the graph we are trying to color is the diameter graph of the polytope. So then Lovash proves something interesting. Lovash proves a lower bound on the chromatic number of the diameter graph of an anti-self-polar polytope. He showed that it's at least n+1 in Rn. So in other words, all these configurations are actually optimal for the Borsuk bound. They don't give me counterexamples yet, but they have at least the Borsuk number of colors that are needed to color them. And he proved this using the neighborhood graph. The neighborhood graph, okay, the Borsuk conjecture says that for any bounded subset of Rn, there is a partition of Y into n+1 sets, each of which has a smaller diameter. And this has been proved. So for finite subsets, this is equivalent to coloring the diameter graph. And Borsuk's conjecture, of course, was proved in dimension 2 and 3. And then Kahn and Kalai found counterexamples in higher dimensions. And then people, Jenrich and Brouwer found examples based on construction of Bondarenko, found examples at lower dimensions and brought the dimension down to 64. So for a dimension between 4 and 63, the Borsuk's conjecture is still open. So so at some point I'm going to have to cut to the chase. So in any case, what I try to argue so far is that these anti-self-polar polytopes are a natural source of potential counterexamples to Borsuk, because according to Lovash's result, they already have a very high chromatic number. But so far, the configurations that we were able to construct, they all have chromatic number 5 on the 4th sphere. And okay, neighborhood complex, I'm going to skip this. That's how Lovash proved his theorem. So now, so let's try to begin to skip to the punchline, to the chase. So the question is, one can ask, is the Borsuk number for R4 equal to 5, or is it equal as Borsuk conjecture, or it is equal to 6? So I claim there are certain considerations here that lead you to think that maybe for R4 the Borsuk number should be 6. In other words, there should be counterexamples to Borsuk's conjecture in dimension 6. So let's denote, so there's a Vajone bound here. So let's denote by capital E of n, let's say n equal to 2, the maximum number of edges in the diameter graph of a substance over n with capital N points. So then it's easy in the plane. It's easy to show that this number is equal to n. In R3, it's equal to 2n minus 2. This was conjectured by Vazhony and proved by Grunbaum, Heppes, and Straszewicz. And Vazhony's conjecture implies Borsuk's conjecture. So the Vazhony's conjecture seems to be closely related to Borsuk's conjecture. Now, the problem with Vazhony's conjecture is that it makes no sense in R4 because, just a second, as we will see on the next slide. So first of all, we can show that the number of edges in the diameter graph of the anti-self-polar polyhedron in R3 is 2f0 minus 2, which is the same as Vazhony's bound in R3. So this just follows from Euler's theorem. And there's a result here that if you have a pointwise extremal set of again diameter below this magic number 2 power of 3, which is the first accumulation point of critical values, then it's actually the number of edges is 2n minus 2, and it's anti-self-polar. I don't remember if I mentioned it. It's necessarily anti-self-polar. Now, what goes against Vazhony in dimension 4 is that there's a cute counterexample. If you look at a point with multiplicity n and multiplicity m on one circle, and then in R4 you get another orthogonal circle, you get the point with multiplicity m on that, then you actually get n squared edges in the diameter graph, which is very far from being linear. But that's because the diameter is equal to pi over 2. But for all the anti-self-polar polytope, the diameter is actually bigger than pi over 2. And I don't have any counterexamples of the type that I just mentioned. And it could be that Vazhony bound will still be linear, let's say in R4, and maybe even related to chromatic number. And so here's what here's the sort of beginning to we're beginning to get to the punchline. For all of the examples of anti-self-polar polytopes that we've been able to find on R4 by using the diameter flow idea, it turns out that the number of edges in the diameter graph is 3f minus 5. So it's this 3 that's the key here, because it leads you to, so using Vazhony's idea for proving Borsuk's conjecture, you would only get 6. You would only get number 6 for R4, not 5. So, and that leads you to conjecture that maybe the Borsuk number of R4 should be 6 and not 5. That's what we say here. So at this point, I'm going to have to skip to the chase. So there are some partial results in dimension 4 toward proving that F1 is bigger than 3f minus 5 that I don't really have time to go over. So let me just skip this and cut to the chase. Okay, so here we're talking about implementation of diameter gradient flow. As I mentioned, you start with a stack in higher dimension, or even on S2 also. You remove suitable points, and then you let it flow with the diameter. And then here's a picture of some implementation of this program that we did. So on the next picture, so here's a bunch of, so we constructed a bunch of examples. So some of them are pyramids, some of them are stacked. Those are A and B. And then we get family C, which have rotational symmetry of order 2, just a reflection symmetry. And we also have 2 configurations that have no symmetries at all. You get this anti-self-polar polyhedron with no symmetries at all, unlike the stacks that they came from. So let me just here's some pictures of these configurations. So here we have a bunch of configurations on the 2-sphere. So again, these are anti-self-polar polyhedra inscribed in, so they're inscribed in the sphere. And they all minima of the diameter, local minimum of the diameter. And here we have 2 configurations which actually have no symmetries at all. These have refractional symmetry. So these are curious looking configurations. You get these special polyhedra in 3 space. And and even a couple that don't have any symmetries at all. We actually have a web page that has pictures of these that are they sort of look, I don't know, I think the pictures of the web page might actually be better than these pictures. These pictures show all the edges, and so it's a little confusing. But in any case, these are the example again in three-dimensional Euclidean space. Borsuk's conjecture is proved. So these examples are a bit of a curiosity. But we also did some work in. So these are the diameter graphs of these configurations. But in higher dimensions, we also did some calculations and developed examples with anti-self-polar polytopes. But so far, there are no counterexamples. They all have Borsuk. They all have chromatic number 5, as predicted by Borsuk. Okay, but in any case, the problem is that, as far as I understood, the programming that has been developed by King Song, it still takes a certain amount of time to develop each configuration. So it's hard to go over many examples. I mean, where many would, I mean, I don't know what many means, but in any case, so far so this is what happens. We start with the deletion in a stack, and then we get new configurations of family C and D. So, for example, deletions on the 4 stack lead to 3 different points for the external configuration consisting of 12 points. So again, this is a discussion back to the case of the sphere, where we get anti-self-polar polyhedra that we saw in this picture. So let me stop here.
Thank you so much. So before we get to questions, let's briefly unmute ourselves. And
Let us what?
I'm going to applaud for you.
Thank you.
Questions for the speaker?
I have one. So what's the precise relationship between anti-self polytopes and pointwise extremal sets such as A sub k and B sub k? Maybe I missed that, but my guess is any pointwise extremal sets become anti-self polytope. Am I correct?
Yes, with the proviso that its diameter is below that magical value that I mentioned, which is the first accumulation point. So there are infinitely many examples under this value. And they're all anti-self-polar, right? But as I mentioned on one of the slides, if you go above that value, then you get immediately examples which are not anti-self-polar. For example, the antiprism on a square. Antiprism on a square is extremal, but it's not anti-self-polar. Lovash didn't work with this restriction because you get a lot of anti-self-polar polytopes which are above this magic value. But in any case, there it's harder to apply the diameter flow because there is no guarantee that the points will not collapse. Okay, below this magic value, we have the theoretical guarantee that the points will not collapse, and therefore we're guaranteed to get new configurations. That's the motivation for working below this first.
Thank you.
I have a question. What is the simplest example of extremal but not pointwise extremal set?
So I get the report here that your internet connection is unstable. Can you still hear me?
Yeah, we can hear you. Why don't you please ask the question again?
So what is the simplest example of extremal but not pointwise extremal set? So there was a can you hear me?
So again, below the bound 2π/3, we know that every external configuration is actually minimum and anti-self-polar.
Yeah, yes.
This particularly is pointwise extremal. Now, whether or not there are configurations which are pointwise extremal but not extremal, I don't know.
Ah, I see. So there are no examples.
I know of no examples, and there could
Okay.
even be families. Theoretically, there could even be families of pointwise extremal configurations of varying diameter, maybe even. But I don't know anything about it. I wasn't able. I wasn't able to prove that the pointwise extremal configuration is necessarily diameter extremal.
And I missed it. This threshold to pi over 3, is it for S2 or it's general?
It's for S2, for S2.
Okay.
For S3, you would have to work with the threshold of R cosine of -1/3.
So
You will get infinitely many examples of extremal configurations under the threshold.
So the threshold is the diameter of a simplex of one-dimensional over.
Right, exactly right.
Okay. Okay, thank you.
You're welcome. So I didn't hear this question before. I guess because of my connection, my connection was unstable, so I didn't hear the question the first time you asked it.
Anyway, you answered it already.
Okay, thank you.
Further questions? Well, if not, thanks so much. And we'll stop the recording here.
Okay.